Light pollution gradients are a reality for us earthbound astro imagers. Depending on where you image, you could get final stacks that have some interesting gradients like these ones. Gradient removal is a very tedious process and sometimes hard to get right, especially when you're first starting out in astro image processing. We do have a few tools at our disposal here in PixInsight. We have automatic background extraction, dynamic background extraction, gradient correction, and the recently implemented multi-scale gradient correction process. We're going to walk through the manual version of the multi-scale gradient process in this tutorial and show how we can very accurately remove these light pollution gradients. Before we get started, I want to show you a couple of resources that you can check out. Navigating to the Process Explorer, you can go to PixInsight.com under Resources, Software Tutorials. The first one there is this multi-scale gradient correction article by Vicente Paris. This article shows how the team was able to go from a CDK20 image that looks like this, with some very complex color gradients, and they were able to correct it out with the methodology that we'll go over today. This multi-scale gradient removal tutorial is largely based on this article, so I would encourage you to give it a read. It's a bit long and technical, but it is well worth your time. Another resource out there that I would like to make you aware of is nightphotons.com. This is a website hosted by Charles Hagan. Charles has some guides here on his website, and one of them is this multi-scale gradient removal process. Charles shows in this article how he was able to go from this image to this. So already we can see how powerful this gradient removal process is, and on some data, it's going to be much faster, more precise than something like DBE or ABE. So let's navigate to a new workspace and we'll get started. I have the workflow outlined here in these process icons, which I will make available if you'd like to walk through the tutorial as I do it today. MSGR is going to use a wide field of view to correct a narrow field of view. So MSGR hinges on the quality of the wide field data. We have some high quality wide field data here today, both in luminance and color. This data comes from Decem Weir in our friendly Cosmos Discord, so thank you to Decem Weir for that. So I like to start with checking the wide field data first. And we can see that in this image, we do have a little bit of gradients here. This is the type of gradient that is perfect to correct with DBE. So I'm going to go ahead and get out a simple dynamic background extraction here. By simple, I mean that I have a low tolerance, I have high smoothing, I've increased the default sample radius to something large, and I've placed the samples in the image plane relatively far apart. So now we can run that. And that did a great job. And then the next step is going to be star alignment. So we'll get our narrow field back out. And I'm going to go ahead and call up star alignment. And we'll put the reference image as our narrow field. And our wide field goes to the target images. Most of the time, star alignment is going to work with default values. If you do have trouble getting an alignment with star alignment, try changing the descriptor type from pentagons to triangle similarity. Sometimes that will work if the orientation of your target is different in the wide and narrow fields. You may also need to use scale differences here and turn this up to 1. But for this data, I think we'll be okay with defaults. I'm going to go ahead and add the alignment preview on our wide field data. Star alignment is going to use the area inside this preview to match to the narrow field of view because we have restricted previews on. So with that set up, we can go ahead and run this. And we can check that alignment. That looks really good. Now that we've corrected the gradients and aligned the wide field image to the narrow field, we can get started working through our process icons. I have them set up in a logical workflow here. We'll name the images, and then we'll decide on star removal. Then we'll do our subtraction of the target signal from the model. We'll remove the smaller scale information from the model, and then we will perform the gradient subtraction. I will explain a little bit of the behind the scenes here as we work through this, so hopefully it makes sense. And with that, let's get started. T1 goes to the narrow field we want to correct. T2 goes to the wide field image that has been aligned. Then we'll create a copy of T1, and this will become the model. Once we get the model, I set T1 aside. The next step is to decide on star removal. Because I'm dealing with a Newtonian dataset with a refractor dataset, I know I'm going to have to remove the stars anyway, because when I try to subtract out these stars from these stars, I'm going to get left with the Newtonian spikes, and that's not going to be helpful. If you're dealing with two refractor datasets and the relative size between the stars and the images is closer, you may be able to get away without doing star removal, but for this data, it will need it. So I'm going to go ahead and remove those stars from both images. With the stars removed, we can then move on to our target signal subtraction. This equation is going to take the T2 image. It will subtract the median value from T2. Then with what's left over from that subtraction, we'll subtract that data from the model with this multiplier. I do want to show a little bit of what's going on behind the scenes here. So we'll remove the multiplier and the model subtraction. And then I'll create a new image. And let's go ahead and run that part of the equation. This is what's left over after subtracting the median value from T2. The reason why we're choosing median for this subtraction is because it's a good correlation to the background value. So we're subtracting the background, and then with what's left, this is what we'll subtract from the model image. This is the reason why we took care to make sure there were no gradients in the original wide field image, because if we were to subtract off the median and there were gradients left in this image, we would still have them in this image. And then those gradients that were left here would get subtracted from here. So we want this to be the cleanest possible data so that we're not affecting the gradients that are in this image. The reason why we have a little bit of noise left over is these are the mean values that fell underneath the median value. These will get subtracted from the model image, but changing these noise scales won't be an issue because with MMT, we'll remove the smaller scales from the model image and we'll only subtract out the larger scales from our final subtraction. So let's get that equation back out. So that explains this part of the equation. The subtraction from the model is self-explanatory. The reason why we have a multiplier here is because there's always going to be a relative difference in the intensities between these two images. So to dial in the subtraction, we're going to need to use the multiplier. I like to start with a value of 0.5 just to see where we're at. And already we're headed in the right direction, but that's not quite enough of a subtraction. We're looking for a nearly perfect subtraction of this target signal from the model data. So I'm going to increase this to 0.6. That's awfully close, but there is still a bit more target signal than I would like left. So let's back up, and I think we can just take it 1/4 step. And that's a nearly perfect subtraction there. So next, we'll pull out multi-scale median transform. What this tool is going to do in this state, I've selected 7 layers, and I'm going to remove all 7 of those layers and get returned the residual layer. At each layer, we have a scale. And to get an idea of what's going on here, think about the scale as the amount of pixels it takes to make up that thing in the image. So if something is 64 pixels big or less, it's going to get removed from this model image. So the reason why it's not going to matter too much to have that leftover mean value in that target signal subtraction is because we're actually going to remove all of the information at those scales anyway. So let's go ahead and run this. And you can see that we're left over with the large scale gradient information. This gradient model looks great. We have our flat donut here. We have the light pollution gradients. At this point, we can go ahead and get T1 back out, which was our original image we were trying to correct. And we can perform the T1 subtraction. We get a very well corrected, nicely flattened image that is free from gradients and ready for further processing. So assuming you have good wide field data, you can expect something like this sort of correction. That is the monochrome workflow. I would like to walk through the color workflow because it is a little bit different. So let me go ahead and close these out. And we'll get out our color data. The difference between the color data workflow and the monochrome data workflow is that in the color data, we're going to have to clear the gradients from 3 channels. There's really 2 ways to go about it. The first way is somewhere in the workflow, there will have to be some equalization of the channels relative to each other. I've seen some tutorials out there that use linear fit at the model image stage where you're trying to generate that gradient model. Vicente Paris talks about using color calibration to begin with, and that's the method that I like to use. So these images have already had Image Solver and SPCC run on them with average spiral galaxy as the white reference. That will set the color channels relatively equally so that when we get to the subtraction stage, we can use the simple subtraction with the single multiplier. If we don't do that, and we didn't want to use linear fit, when it gets time to subtract the target signal after choosing star removal from our model image, we'll have to do this multi-channel subtraction, and that's just where you'll have to adjust the multiplier for each channel, and that can be very clunky and hard to dial in. So I like to set the levels early on, following Vicente's methodology by doing color calibration, and as long as you do the same color calibration to both images, it will work well. It won't work well if you're using SPCC and you're changing the white references for each image. You do want to make sure you do the same color calibration to both. So let's start at the same place we did with the monochrome data now that we've color calibrated these. And we'll check the wide field. Again, it's a great looking image. It's got good SNR. There is a little bit of gradient here, so we can use the same DBE instance from the monochrome workflow. We'll just go ahead and run that. And that correction worked out well. Then we can move on to star alignment. Narrow field becomes the reference. We're going to go ahead and leave the default settings. I will have to add that alignment preview here. And we can go ahead and run that. And let's check that alignment. It's a very nice alignment, so we are now ready to walk through the process icons, just like we did with the monochrome data. Let me set that aside for now. T1 will become the narrow field we want to correct. I almost always forget to do this when I'm doing multiple data sets to rename these. So T1 will become the narrow field we want to correct. T2 goes to the wide field that was aligned. And then we'll create a copy of T1, and this one will become the model. When we have the model, we can set T1 aside. I already know I'm going to have to remove the stars based on the monochrome data, so we'll go ahead and do that. And with the stars removed, we can go on to the simple subtraction since we already did the color calibration. And again, I like to start with a value of 0.5. We're already pretty close, but we're darkening in the center there, showing a bit of over subtraction. We don't want to over subtract the model because when we remove the smaller scale layers, we'll be left with a dark spot there. And if that dark spot remains, it will brighten the image when we do the final gradient correction. So we really want to dial in the target signal subtraction here. Just want to back up a little bit. I think we can back up a quarter step here and just go to 0.475. That's a really good subtraction. I'm going to see if I can't get that just a little bit better. To my eye, there's a little bit of signal that's been brought back. I want to see if I can get that just a little bit better by going to something like 485 maybe. That is much better. So we'll go ahead and remove the smaller scales with MMT. And that's a great gradient model. So once we have this, again, we can call back T1 and we can do our gradient subtraction from it. And we can see how we went from something like this to this. When dealing with color data, I always like to check that we're not affecting the target's color. Because if we are, that'll show that our gradient model was not very good. So let's go ahead and go back and forth here with this and check the color on those spiral arms. And that color remains consistent. We are removing the green from around the galaxy, but that color remains. So that's a really good correction. And just to reiterate, let me close these out and we'll look at both of these. For the luminance channel, we went from this to this. And the color channel, we went from this to this. You can see how powerful this method is. Anytime I have good wide field data, I like to use this method. That is MSGR as I do it. The two places where you can really dial this in and get a really good subtraction are going to be in the simple subtractions multiplier. And in the MMT run, you can change the layers parameter to affect smaller or larger scale gradients. I would be careful, a word of caution here, if you start to get too low on your layer selection, if you get down to layer 5 or 4, something like this, you're only affecting pixel sizes of 8. So if something's made up of 8 pixels in the image, it's going to get removed, and anything above that will be affected. So at that point, you would probably be affecting the galaxy in a way that you wouldn't want to. So there is a point at which you could go too low with this, but 7 layers typically works out pretty well for me. And if you need to, you can increase or lower that parameter as needed by the data that you're working with. As a reminder, I will be making these process icons available to you for you to work with. I hope that helps. Happy processing and clear skies.